Hello everyone, welcome to today's video. Today we're going to focus on direct preference optimization, which is a post-training method that fully bypasses all of the reinforcement learning stuff that we've been working on lately. Now, this method is very useful because it is very cheap and it actually ends up condensing all of the RL stuff into a simple classification problem, and we're going to focus on that once we read the paper. This video is going to include the paper reading as well as the actual implementation. Now, in the paper reading, I will break down the math. If you're not really interested in that, don't worry. The paper's implementation details are extremely simple and it's a very easy implementation. Now, in the previous video, we worked on building RLHF from scratch. Now, RLHF utilizes PPO, and we saw how that worked in language modeling, in which we had four important models that we loaded into memory while training our main model, right? We had the policy model, which is the actual model that's being trained, alongside the reference, which was the frozen supervised fine-tuned model, the reward model, which outputted our scalar rewards, and then our critic. Now, you can imagine, and you guys saw, all these pieces are very interconnected, and it's a very complex process. And you're going to see from this video and from this paper that this process of RLHF can be condensed into a simple classification problem. Now, this method is very important for us. Like I mentioned before, it's really cheap, and a lot of open source labs started using it when it came out. And yeah, it's really, really interesting to see. So I'm going to jump straight into it. Let's start this off. So the name of the paper that introduced this is Direct Preference Optimization. Your language model is secretly a reward model. This is a really cool statement, and you guys are going to see how exactly this works. But this method, using this method, we go from having that really complex PPO setup of, as I said before, the policy, the reference, the value, and the reward model. All that gets condensed to just a policy and a reference, and no need for these two right here. Because again, we are bypassing the whole idea of using reinforcement learning here. And we basically find a way to set up the situation of having, if you guys remember the objective of the reward model, it's to minimize the loss function between, or yeah, to minimize the loss function between a Y winner and a Y loser given some X. We utilize this to basically set up a classification style loss function in which the policy learns this by itself without the need of having to go through a whole reinforcement learning environment, without having to need a reward model. And yeah, we'll break that down. So let's start off with the abstract of this paper. While some language models learn broad world knowledge and some reasoning skills, achieving precise control of their behavior. Remember, this is at the end of the day, this is the whole point of all of these reinforcement learning algorithms. It's to promote the alignment into what we want the model to actually do and respond to. It's difficult due to the completely unsupervised nature of their learning. Here they talk about the existing methods, basically talking about RLHF and how that is the method that is widely used. But as we spoke about, and as we saw in our own implementation, it's a complex and unstable procedure like they talk about here. And it is pretty expensive. So what they do in this paper is implement this algorithm. Again, they call it DPO, which is very lightweight, especially compared to RLHF. And they basically show that DPO is on par with the existing PPO algorithms, especially at the time. So what you're basically getting is similar performance at a way cheaper price, a way cheaper system, which is a win. And yeah, so I mean, you see it here. I don't think these charts actually do like the best explanation of how this works. So we're going to go straight to the math and all of that stuff. Here in this introduction, they just talk about language models, very smart pieces of machinery, and RLHF. But in this paper, again, to optimize a model to adhere to human preferences without RL, they propose DPO. Related work, again, this is just talking about the stuff that was before this paper, but here we are in the more important bits. You may be wondering how this, which is basically our Bradley-Terry model, right? This is the loss that we used when we implemented our reward function, in which we minimize, or we have a negative log likelihood of the logarithm of the sigmoid of the reward of the winner minus the reward of the loser. And our job is to get this number as high as possible so that this minimizes the loss as much as possible, right? What we do is, they talk about it here, make it very simple for us. If the model rewards, if the model receives as input a good response relative to the prompt, it gives a high reward. And then if it gets a bad response, it lowers the score, right? It gives a low score. The way we define high and low is centered around 0. So basically, we normalize the reward so that a good reward is given a positive score and a bad reward is given a negative score. And then if you guys definitely recognize this equation right here. What we want to do is maximize the reward, right? Now we have a custom reward in RLHF, which is our reward, our actual reward minus this beta hyperparameter times the KL divergence of the policy model and the reference model. Basically, we don't want our policy model to become a reward hacking system that just produces things that result in higher rewards. For example, it might learn that longer responses result in longer rewards, so then it just starts filling up with random text. We don't want it to start doing that, so we want it to stay close to this reference model. Now, this reference model, they initialize it from, right here, from pi SFT. So that's basically our model after supervised fine-tuning. So this shows good like question answer abilities and things like that. We want it to stay to that base nature. And so this is what ends up being our loss function for our policy. I'm sorry, not our loss function for our policy, but our reward, right? Now, this is where DPO comes into play, right? Their goal, again, was to derive a simple approach for policy optimization, basically using the preferences directly without using reinforcement learning and without using a reward model, right? And without that whole complex process. And so the way we have to think about that is we have to mathematically find a way to make a loss function for our policy given our reward model. Now, here is the point where a lot of this doesn't necessarily matter for the implementation. If you guys want to know what the implementation is, and just jump straight to the project, honestly, this is the point, right? You guys can skip straight to the implementation from this point forward. Basically, it's just this, right? It's just this loss function. We want to minimize. Just look at how similar this is to the reward model's loss function. The log of the sigmoid of beta times the ratio of the winner of the policy over the reference winners minus the policy over the reference losers. We're basically doing the same thing, right? Finding the difference between the winners, and the winning response and the losing response. And what we do this, the way we do this is with these very, how can I say it? These very recognizable pieces of math, right? We've worked with this kind of ratio. If you remember, this is so that they don't stray too far apart, right? We talked about that. The beta is the same hyperparameter. We're basically getting this KL score and then this score, subtracting them, and we want to get this as high as possible. We want to get the difference between the two as high as possible. That's basically it. I mean, that's our implicit reward, and implementing it is extremely simple. And this is basically how we fit the goal of PPO using the reward model into just a classification problem. So from this point forward, if you're only interested in the implementation, we can jump straight to it. But I'm going to focus on the math of how we even get to this point and think about, like the actual reason why this works, right? So I'm going to go down to, you guys can read the experiments and all that. I'm going to focus more on the actual math behind this. Let's pick a blue. Let's see, right here. So this is how we actually derive the DPO loss, right? Now you're going to see that the math ends up being a lot of just simple algebra, and it's just a lot of little math tricks to get us to the point that we're at. And yeah, let's start off in this point right here. You guys recognize this. We literally just talked about it. This is our goal in PPO, or sorry, our goal in RLHF is right here. We want to maximize this reward minus the KL divergence of, or well, minus the KL penalty, which is this whole second part right here. So now you basically see them break it down here. If you recognize this this part, this is how we actually write a KL divergence when it comes to the code. A KL divergence is literally equivalent to the logarithm of the A variable, and or like the A distribution and the B distribution. And then this is also the same thing as log A minus log B, which is why in the code we literally write this out as our reward minus our beta times, if you guys remember, policy log probs minus reference log probs. And that way, that's how we basically see how different the two probability distributions are. And so here in the math, we break it apart like that. And then this step right here, this is more of like an aesthetic step, right? Realize that we go from a goal of maximizing this to minimizing this. And so what we do is we multiply everything by -1 over beta. That's why we have -1 over beta here, and then we have nothing here. So it's just like an aesthetic thing. And the more complicated bits come here, this part right here. Like, how do we jump from here to here, right? You're going to see this variable z. Right now, it doesn't mean anything, but it will. So, yeah. Now, let's think about our actual, basically our actual goal with this, right? We want to derive the optimum, like the optimal, the optimal value, right, or the optimal variable of a KL-constrained reward maximization objective. Basically, here's our KL constraint, and basically what we want to do is we want to make everything here basically like a KL penalty. Right? And so, as we talked about, a KL penalty is kind of like this, the log of A over B, but this obviously isn't in that style, right? Because we have the logarithm of the distribution of the policy and the reference, but then we have this minus bit, minus 1 over beta times the reward. This part doesn't fit a KL divergence. So we can't make this internal part into a KL divergence. There's no logarithm there, right? So the way that we kind of fit this to work is we set this equal to, and which it factually is equal to, the logarithm of Euler's number to whatever number this is, right? Because we know that the log of E to x is equal to just x, right? That's basically what we do here. And we convert this to log of the probability distribution here over the references distribution. And now we basically have minus log E to this value. And so what I talked about before, remember, A, let's do a different color, log of A minus log of B, because we literally just went over this, is A over B. And so we divide this portion. What we end up getting is this logarithm. We have this stays as the denominator, but what we end up having at the bottom is pi ref y given x times the times this beta r x and y. Cool. And now you're going to see something. This denominator portion is it not the same as this, basically? This x basically just means Euler's number, and whatever's in here is this. So when you see x of y, this is the same as e to the y. And so realize that. So this is what z of x is, this denominator portion. Now let's talk about why we have 1 over z of x and this log z of x here. Let's see if I even have space for this. Okay, so remember that for this to work out, the top has to be a probability distribution, and so does the bottom. Now, for something to be a probability distribution, let me just put a probability distribution, everything has to equal, once added, everything has to equal to 1, right? Now, since we added this bit right here, we don't necessarily have for certain that everything will be added to 1, right? Because this is we know for sure this is a probability distribution. This adds up to 1, but this could add up to maybe 3 or something. And now we have a denominator of 3. What we want is not a denominator of 3, I'm sorry, but this is a multiplying factor that may or may not change the full addition to not be 1. So let's say our results, our denominator is equal to 8 or something. Obviously, if you want to set x equal to 1, what you do is divide it by x, and that's equal to 1. So in this case, we divided by 8, and that's equal to 1. And so that's why you realize what they have here is basically, in the denominator, they basically have 1 over z of x times this part right here, which ends up being z of x. And now you know this is equal to 1. Or like the addition, the summation of it is equal to 1. So that's basically that. And now this minus log of z of x is because of everything we've been adding in here, because not only have we added this, but then we also added this 1 over z of x. What happens is we have this log, I believe, this distribution, and then we have this distribution, z of x times pi ref, the reference model's distribution, times e to the minus 1 over beta. We have this very complex equation, right? Realize we've been adding stuff in. So, and what we want to do is we want to make sure that this is still equivalent, mathematically equivalent to what we had up here. Because again, we want to represent this whole internal bit in another form, but we still want to maintain the validity and maintain this to be the same. So realize that here, given all the rules that we've been talking about with the logarithms, this is basically equivalent to the logarithm of the policies distribution minus this, minus, right, because these are all in the denominator, this, minus this. And now we can flip this into a positive, and when we can also turn this into what it used to be. And then, you know, subtractions, we're going to keep it as, we're going to keep the subtraction of these two as a logarithmic, like division. And so what we end up with is logarithm of our policy over our reference minus 1 over beta and our reward plus logarithm of z of x. Like I said, we want to keep this in the same. So this part is this, right? But now we have an additional logarithm of z of x factor. We'll put this in icy blue. We have this extra bit. So again, if we want to keep everything mathematically the same, we have to subtract this bit out. And that's why what we end up with is this internal equation, which is basically the log of our policy over 1 over z of x minus log of z of x. Hope that part made sense. And now, what we're basically defining is, we're defining this part, this pi star is our optimal policy. Basically, the best policy we can have. We define it as basically the denominator that we found down here. And so this is a valid probability distribution as the optimal policy distribution is greater than 0 for all of y, and then the summation is all 1. And then since z of x is not a function of y, we can reorganize this to be, like we talked about, we're changing the way we're looking at this equation into a way that we don't need the this reward to come from an external factor. And so here we have the goal. We change the objective to minimizing basically this, which ends up being the KL divergence of pi and pi in the optimal policy minus the logarithm of z of x. And now in this instance, right, z of x, since z of x does not depend on the parameters of the policy, the minimum is achieved by the policy that minimizes the first term. Yeah, just this term, we reach it. And then the KL divergence reaches 0 if the two distributions are identical. And so the optimal solution, the optimal policy, basically the best policy we can get, is equivalent to this. This is the derivation. That is what we talked about, right? The 1 over z of x, the reference policy, times the exponent of 1 over beta r x and y. Yeah. So basically, this logarithm is ignored in this instance, like our optimal solution, because, for example, if we're finding the local minimum of a graph, for example, or the location of the local minimum of a graph, we don't care about this plus 5, right? We just want to know where the x is at. That gives us that minimum. Yeah, and then in this case, that is 3. Same kind of principle here. And now, here we have, so here we have the equation for our optimal policy. And now let's derive the actual loss. So if you guys remember the Bradley-Terry model that we used, this is basically saying like this, that I is greater than j, and that's equal to this bit right here. So I mean, in this instance, it's just the probability that or that YW is greater than Y loser given X. If you guys remember, it was equal to the Bradley-Terry we used was this, but the original Bradley-Terry, what it is this right here. And it's basically saying E of the winner over E of the winner. What is it, minus? Sorry, plus E of the loser. So let's look at this. We can express the ground truth reward through its corresponding optimal policy. So now what we want to do is we want to find the new reward given as a function of the policy, right? So what we have, I'll show you guys how to reach this point. The way you reach this point, if you guys remember now, here we have our optimal policy is 1 over z of x times the reference distribution E of 1 over beta R. Here, let's just say R star, because this is the reward of the policy of our optimal policy. What we do is we multiply both sides by z of x. Again, like I said, this is a lot of basic algebra. R star is up here. And I mean, we divide both sides by this. So what we get is z of x, the optimal policies distribution over the reference policies distribution, is equivalent to e to the this. And so what happens at this point, we just set both. We want to obviously isolate this, right? And the way we do that is we multiply both sides, or we get the logarithm of all the sides, right? And so we also know the same way with the division, the logarithm of AB is equal to log A plus log B. We're going to do that right here. Basically, when we get the logarithm of this, or I should do it in a different color, log here and log here, this ends up giving us log of z of x plus log of, and I'm missing something here. Yeah, 1 over b, I'm sorry. Or 1 over beta. Log of the optimal policy over the reference policy. No, sorry, the reference model is now equivalent to 1 over beta r star xy. And then, I mean, you see how the beta just goes to both sides. You just multiply by beta. Now you have beta at the front. You don't have this anymore. And then that's what our theoretical optimal, or the reward would look like through its optimal policy. And so remember this here, right? But now that we have our optimal reward, all we do is just substitution, right? And so we have these as these substituted. And so what we end up here with here is A over A plus B. Realize this is A, this is A, this is B. That what that ends up being is that ends up being equivalent to 1 over 1 plus B divided by A. And so B divided by A, in this case, you know with the logs how that ends up being. And so that's why we have the subtraction here. And then let's think about this. We now end up with 1 over 1 plus e to the, let's just make this equal to x, I guess. Or no, not x. Let's make it equal to z. 1 plus e to z. What does this kind of remind you of? This is the same thing as a sigmoid function in a way, right? 1 over 1 plus e to the negative z. So what we do is, you notice there, here the y2 is at the front. We just negate this. And so what we end up getting is just the sigmoid function of z. Or well, negative z in this case, because I put everything inside the parentheses as z. And so that's basically the loss function for us, right? I mean, let's go up to the actual loss. This is basically how we achieve that loss. Here you see the sigmoid, and then here's all of this. And yeah, so that's how you derive the DPO loss. I think it's a very clean math. Some parts like this jump between the last step of equation 12 and the step before it. This whole partition function part was a little confusing to find at first, but I believe this makes a whole lot of sense. And so the actual implementation you're going to see is super easy. And so I'm going to stop sharing my screen here, and we're going to go straight into the code. First thing we're going to do is we're going to start the implementation, right? So I want to show you guys something. Where is it? Is this the paper? No. Where's the paper? Oh, right here. In the paper, all the way at the end, they have a PyTorch implementation of it. And I mean, you guys saw the math again. It's just implementing one loss. It's nothing crazy, right? It's just returning this loss right here. And so we're just going to do this in JAX just to differentiate it a bit. So let's start with DPO. First thing we should do, and I should let you guys know, is we're going to have the same transformer.py and policy.py. Basically, this is what we did for our RLHF. We're going to have the same transformer and the same policy, but we need nothing more. Right. First steps, we're going to implement import JAX, import jax.numpy as JMP, and then from Flax, we're going to import NNX. Now, we do have the hyperparameter. Let's just define it up here. And we're going to set it equal to 0.1. Reason being, in the paper, they use beta as 0.1, unless noted otherwise, right? Here they use 0.5. In the previous implementation, we did use 0.1 as well, I believe, because this is the same KL divergence hyperparameter that we were using, or the KL penalty that we were using beforehand. And so what we're going to do is we're going to define a DPO loss. And in here, what we're going to pass through is the prompt. We're going to pass in our policy model, our reference model, our winner Y, and our loser Y. And so let's think about, again, what we're doing. This ends up being, right, we need the log ratio of the winners. Let's look at this here. Right? We need the ratios of the policy, and then the ratio of the reference. But we need the winner and the loser ratios. Actually, this is a bit different on how I implemented it. I implemented it more like the actual, math, I believe. So let's actually look at the loss. Let's look at this. It's the policy divided by the reference for winner, and then for the loser, same thing. So what we have here, we're going to take, basically, we're going to define like the ratios. And we're going to have the log ratio of the winners. Or let's just say the policy log probs winner, right, of the winner minus the reference log probs of the loser. And then we're going to, not the loser, sorry, also winner. And then here we're going to have the log ratio of the loser, and that's equal to the policy probabilities for the loser minus the reference log probs loser. And so looking at the paper, right, we can take this beta out, right? This is multiplied between the two of them. What we just want to do is subtract the both of them. And I guess I'll call that the logits, right? So here we have our actual loss, right? And then we're going to have our logits is equal to beta times the log ratio of the winner minus the log ratio of the loser. And then the loss just ends up being the mean of the log sigmoid of the logits. Bad typing day. And that's what we're going to return. And so how do we get the log probabilities? Well, you remember this function right here, log probs of. This is don't worry, don't worry about the notes. This is I got this from the actual repo that I worked on, so this is a little bit old, but this is how we get the log probabilities given the tokens that are in the responses. So we're gonna have to do that for each model, right? So we're just gonna make a per token log probs per model, and then get token log probs. Here we're gonna take a model and a y. This is just gonna be an internal function where we do the whole thing, right? And so the whole idea is to do policy log probs winner is equal to get token log probs of our policy and our y winner. And then we're going to do reference log probs winner, where we pass in our reference model. Sorry. And same thing here, right? Policy log probs loser. Policy and y loser. And then same thing here. Loser. Token log probs y loser. And so here we have our function here. So first thing we want to do is we want to get the full sequence. And the full sequence, jmp.concatenate. We're going to concatenate x and y. And so we're going to pass this through the last axis. Because remember, this is batch and sequence length. So we're going to have the full sequence, and then we're just going to get the logits by passing it through the model. And that's how we gather the log probs. We get the log softmax for the logits along the last axis. And so now we're going to define the actual targets. Remember, the targets are one ahead. So we copy the same list, but we have it one ahead on the second axis, and then we get the log probs from there. Log probs of this. And so we get the token log probabilities now of the actual tokens that were that was in the response. JNP.takealong access, sorry, not JAX, JNP.takealong access. And we get log probs. We also pass in this. Along the last axis. And we squeeze -1. And yeah, this is basically what we return. What do I even import, man? Token log probs. Now there's still some masking stuff to do, right? We're gonna get the length of the prompt. And we're also gonna get the length of the actual response. And we're gonna create a mask for this. We've done this before, this kind of setup before. And so now we're going to get the shape of token log probs. And what we're going to do, we're going to set our mask equal to wherever the mask is greater than the prompt 1 minus 1. And minus 1. Yeah. And so the mask, we return this with the mask, basically. We get the token log probs times the mask. And we sum this along the final axis. And yeah, I mean, this is basically just the whole implementation. This is how you implement DPO. The training sequence, I'll show the training sequence as well. So here, make a new file, train.py. And we're going to do the same thing as always. Import jax.numpy as JMP. And from flax, import nnx. In this point, I'm going to show basically what I've learned of how to use nnx. I think this is the cleanest code that I've had thus far. And it is a simple implementation. So the first thing we're going to do, as always, is the train step. Now, remember, there is no RL here, so no rollout, nothing like that. This is a relatively simple thing. And so here we're going to pass full models. Forget about graph depths. Forget about states. We're going to let nnx deal with that. And we're going to pass in the data. And so here is our batch, right? We unpack this from the batch. And then here we define a loss function. And we're going to pass in the policy, right? Since that is the model that we're actually training. What are we going to return? Well, we worked on a whole DPO loss back here, right? So what we're going to do is we're going to import from DPO.DPO import DPO loss. And here we're just going to import return DPO loss with the policy. Actually, I believe the X was first, then the policy reference Y winner and Y loser. And so now we collect the loss and the gradients through nnx.value and grad. And here we have the loss function and we pass in our policy model. And our optimizer, I forgot. Here we have our optimizer and we update the policy with the new gradients that we had. And this is where we return the loss. And now this whole thing is jittable. So we do at nnx.jit, not jax.jit, just nnx.jit. There's nothing static here, so we just keep it as is. And then we do the same for our epoch of training. Remember, this is an offline method, so we already have all the data that we need, right? We don't need to, we're basically combining the step of training the reward model with all of that PPO stuff. We're just collapsing it into one. And you're seeing how simple this is, right? It's a simple classification thing. And so for each batch in the data, what we do is we collect the loss and we just append it. Sorry, policy. What are the reference? Optimizer. Batch. And so we just append this to loss. To losses, and we just return losses. I mean, again, this is just so simple. This is basically the whole training loop. And so I'm going to copy and paste what I have in the repository as the test. So I'm going to copy this in. We're going to import optax. Oh, I don't have any of these things installed. But for your test, what you're going to want to do is import all of these. This will just be for policy and for transformer. In this case, we don't have optax installed. Don't worry about it. And so here we define our random number generator, our key, and our configuration. We just define our models, just two models, and our optimizer. This is how you define them in nnx. And so, yeah, I mean, that's how you would test this out. But basically, this is it. I mean, let's look at it. 7 to 25. That's 18. And then this whole file is 43 lines. So DPO can be implemented in under 60 lines in JAX. And I probably didn't even do it the best way possible. So this could all probably be like 50 lines of code. But thank you guys so much for watching. I hope you guys found some value in this video and saw, more importantly, how DPO bypasses all of the complexities of PPO, we're basically doing the same exact thing, just with no reinforcement learning. And this is very helpful for alignment stuff. Now, DPO does have pitfalls because obviously why winner, why loser, that comes more to play when it comes to human preferences. But for math, for code and things like that, there are verifiable results. There is no preference, maybe in code style. And that's actually an interesting thing to look at. I never thought about that, but until like right now. But anyways, for math, for example, we want the model to actually like discover its reasoning traces. And that's why PPO is still used for reasoning, and GRPO, which is what we're going to discuss in the future videos, what DeepSeek introduced last year, very widely used for reasoning tasks. But for post-training and alignment, DPO gets the job done without any of the fluff that PPO brings. So thank you guys so much for watching, and I hope you guys enjoyed.